GMR is a spent catalyst recycling facility, the only one in North America to be able to efficiently recycle hydro-treating and hydro-refining catalyst. GMR uses proven technologies to process spent oil refinery catalysts. The two types of catalyst recycled at GMR are HDS, which stands for Hydrodesulfurization Catalyst, and RDS, which is Residual Desulfurization Catalyst. HDS contains molybdenum, nickel, and cobalt. It is generated at all petrochemical refineries in North America. RDS is oily and rich in vanadium, nickel, and molybdenum. RDS is mostly generated in the Canadian heavy oil upgrading operations, but also in the US. Gladio Metals Recycling, Wall of Knowledge. The first step in the process is material receiving, inspection analysis, and acceptance. GMR can receive material via truck and rail. Most HDS material arrives via truck, while most RDS arrives via rail. When material arrives at the facility, each shipment is assigned a lot number and then carefully inspected to ensure it has proper paperwork, and one or more samples are taken from each container. These samples are analyzed at GMR's on-site laboratory for metals, carbon, and sulfur. If all characteristics meet our standards, the material is accepted. As part of our new process, catalyst will be screened and de-oiled by processing this material through a thermal desorption unit. By removing the oil, the spent catalyst will have a lower BTU content, allowing for lower roasting temperatures within the two multiple hearth furnaces, resulting in improved process control and extended refractory life. Once de-oiled, a homogeneous blend of HDS, RDS, and soda ash will serve as the feed for the furnaces. The next step in the process is roasting. The blended feed will be conveyed through a totally enclosed conveyance system to the top of the furnaces. GMR has two 12-floor multi-hearth furnaces, or MHF. The design of the MHF is such that it moves material from floor to floor by raking it toward an opening in the center, and the next floor will rake toward an opening on the outer edge of the floor. This in-out flow promotes a high residency time in the furnace at a high temperature. This high-temperature process removes organics such as carbon and sulfur from the catalyst. These organics are carried out in the off-gas duct and further eliminated by the additional pollution control equipment. This equipment consists of a post-combustion control chambers, SO2 scrubber, and baghouse. The SO2 scrubber and baghouse were the last major CAPEX improvements, totaling $50 million. It was commissioned in 2013. Once the roasting operation is completed and all organics have been removed, the resultant material, calcine, is fully oxidized and is ready for hydrometallurgical metal extraction. The first step of the hydrometallurgical process is grinding of the catalyst in a ball mill to expose a larger surface for the leaching process. In the leaching process, with the help of reagents, the molybdenum and vanadium go into solution while the nickel, cobalt, and alumina stay in their solid states. This leaching process is done in a series of tanks. Once the moly and vanadium are solubilized, they will go on to the next step for further refinement. The remaining material will be fed through a filter press to remove the solids. These solids will contain the nickel, cobalt, and alumina, and are now called alumina concentrate, or acetyls. The acetyls will be the feed for the electric arc furnace. We will come back to acetyls further in the process. The solution containing moly and vanadium, also known as strong solution, will continue onto an impurity removal process called MAP treatment. This step removes arsenic and phosphorus using a magnesium-rich reagent, therefore the name MAP: magnesium, arsenic, phosphorus. The residual is called MAP cake. MAP cake represents approximately 1% of the received material due to its lack of value. It is sent to a landfill. The strong solution containing the moly and vanadium will go through the first precipitation tank. This step will target vanadium first. With the help of reagents, it will take out the vanadium from solution and form a wet cake that will be recovered in a vacuum filter belt. This cake will then be sent to a decomposition furnace to remove impurities and onto a fusion furnace to complete the oxidation phase to form vanadium pentoxide, V2O5. The vanadium comes out as a hot liquid metal from this furnace, which is transferred to a flaking wheel to form V2O5 flakes ready for packaging. The purity of the V2O5 is greater than 99%. The remaining solution will be rich in moly and, like the previous step, will be precipitated, form a wet cake, and then will be extracted via a vacuum filter belt. Next, it will transfer onto a kiln for drying and oxidation. This will result in powdered molybdenum trioxide, or MoO3, with a 98% or greater purity. The main markets for these products. V2O5 can be sold into the aerospace superalloy industry, where it is used as an alloying agent, which requires a high degree of purity. The largest market, however, is for conversion into ferrovanadium, an alloying agent for steel manufacturing. Other important markets include chemical applications such as catalyst and developing battery technology, vanadium redox batteries. GMR's moly trioxide has been sold for decades into the fresh catalyst manufacturing industry for production of new catalysts. Catalyst manufacturing starts a new catalyst life cycle, so that once it becomes spent, it can eventually return to this facility for recycling, which we call full circle recycling. The remaining solution will go onto the solvent extraction process. This step removes the remaining metals from the solution and circles them back to the beginning of the leaching process for another pass. The clean water will be sent to GMR's water treatment plant for additional treatment to meet standards for permitted outfall. The pyrometallurgical process consists of a 10 megawatt electric arc furnace, or EAF. The EAF takes the AC tails generated toward the beginning of the hydro process as its feedstock. The first step is to dry the AC tails. Once dried, they are sent to a silo for storage. Two other materials act as reagents in this furnace: pulverized lime and metallurgical grade pet coke. The three ingredients are then blended and fed into the EAF to metallurgically extract the nickel and cobalt. The reaction that occurs inside the furnace allows the nickel and cobalt to be separated from the alumina. Alumina makes up most of the material fed onto the EAF. The difference in densities allows for the nickel and cobalt to flow to the bottom of the furnace, while the alumina concentrates in the top. Alumina is then extracted from one side of the furnace, while the nickel and cobalt keep building up at the bottom of the furnace, where they eventually reach the tapping point and are extracted. It takes approximately 10 to 12 alumina taps to have a full nickel-cobalt tap. This pyro process also has pollution abatement control equipment, which removes the off-gas solids. The alumina forms a slag, also known as calcium aluminate. Once the calcium aluminate is physically broken into smaller pieces, it can be sold into the steel industry as a fluxing agent. The nickel-cobalt alloy is sold to a nickel-cobalt smelter for further refining. This alloy contains approximately 50% nickel and 10% cobalt.